Swayam Prabha. Digital India. Educated India.
Today we are starting a new chapter that is known as MOSFET. Okay, MOSFET stands for metal oxide semiconductor field effect transistor. Okay, so MOSFET stands for metal oxide semiconductor field effect transistor. As we have discussed BJT before, like BJT, it is also a transistor device, but the working principle and structure is different. So we will see that we will also discuss its application as a switch and its application as an amplifier. Okay. Now to start with, I would like to emphasize that whatever our integrated circuit revolution occurred in last 60 years or so, it is because of this MOSFET. Okay, it is not because of BJT, rather it is because of MOSFET. Although the concept was initially built around 1930 or so, but people managed to make or fabricate MOSFET much later than BJT. I think it's around 1955, 1960 people managed to ultimately fabricate the MOSFET, though the concept was much before than BJT was conceptualized. Okay, but its fabrication was difficult. Now the reason it is, although it has the same application like as a switch or as an amplifier, but it surpasses or it overtakes BJT in integrated circuit simply because we can scale down this device. Okay, means we can reduce the size of this device. Okay, so whatever we see around us, any electronic gadgets, the heart of the integrated circuit is basically MOSFET. Okay, for example, we have billions of transistors, that is the MOSFET is possible to make, and we have our present days microprocessors, memory chips, or on a single piece of silicon contains several millions, even billions of these MOSFETs. Okay, so MOSFET is the heart of integrated circuit. So whatever electronic gadgets we see today is its compactness, its low power, its very fast operation, everything is because of this device. Okay, so it is a very important device as far as the electronic revolution is concerned. So we should learn what is the device structure and how it operates. Okay, so it is a very important device. Now, as the name suggests, it is metal oxide semiconductor field effect transistor. So the heart of this device contains this metal oxide semiconductor structure. Okay, metal oxide semiconductor structure, and how it operates or works using a field effect. So using a field, we will be able to control the flow of current in such a device. Okay, and that is how it operates in a nutshell. Now to start, let's just brush up a capacitor, how the capacitor works. Okay, because that's the heart of any MOSFET structure. So we know usually a capacitor, we have two metal layers. Okay, all metal plates, and these two metal plates is separated by a distance, say d. Okay, and what we do, and this usually in between these two metal plates there is an insulator. Okay, and what we do, we connect these two plates with a supply voltage. Okay, say we can connect like this. So what will happen, that a negative charge will develop in this plate, and that will mirror positive charge in the other plate, right? And there will be electric field between this positive plate and negative plate through this dielectric which is present between those two plates. It is how the capacitor works, right? Now and of course there is insulating dielectric constant, which is also very important role to play as far as the capacitance of this structure is concerned, and so on. Okay, now what about MOSFET, that is metal oxide semiconductor? Okay, so if I try to replicate this capacitive structure in a MOSFET, so I have a metal, I have a oxide layer, that is basically my insulator, and I have a semiconductor. So this is your MOS, or this is, so this can perform, this structure can perform as a capacitor. Okay, so there is a metal layer on top, right? There is a oxide layer in between this metal layer and a semiconductor. So what we can do, say for the time being we are assuming this is a p-type substrate. We can have the same discussion considering this is an n-type substrate also. Okay, now if we connect a supply voltage like this, okay, then what will happen, negative charges will form on this metal plate, and that negative charges will attract holes. Okay, so holes will move towards this oxide silicon interface. Okay, so we will have a layer of holes very close to this oxide silicon interface, right? And that forms our layer of positive charge, right? And so there will be an electric field between this positive plate and negative plate. So this is your one plate. Okay, effectively this is a plate that is say M2, and this is my M1. This is not metal, but I am just putting a name M2. Okay, so don't bother about that name. So what I try to convey, like if I can fabricate a metal oxide semiconductor structure, so to start with I will have a p-type substrate or n-type substrate. Okay, for the time being let's concentrate that I have a silicon substrate which is p-type, then I have deposited or grown oxide on top of this silicon substrate, and on top of that oxide layer I have deposited a metal layer, right? Now if I connect supply voltage between this metal and this semiconductor in such a way that this negative terminal is connected to metal and this positive terminal is connected to my silicon p-type silicon substrate, then what will happen, negative charge, a layer of negative charge will form on the metal surface, and that basically mirror or that basically attract positive charges. So what are the positive charges here in the p-type substrate? Those basically holes. So holes will move towards this silicon oxide interface and form a layer of positive charge. Okay, so effectively it acts as a capacitor, right? And there will be an electric field between these holes and this negative charge metal plate, and obviously the electric field direction according to our concept from positive to negative side, right? Now if we increase this, if we keep on increasing this voltage, then the number of holes accumulate here will increase, right? Because then more number of negative charge is on the metal surface, so that will attract more number of holes. So this particular phenomenon is known as accumulation. Accumulation. Accumulation, right? Now what will happen if we reverse the polarity, or if we use a voltage source which in such a way that positive terminal is connected to your metal and negative terminal is connected to your p-type substrate. Okay, so let me draw it once more. So I have a metal, I have a oxide, and I have a p-type substrate like before. So this is oxide, this is metal, and what I have done now, I am applying a voltage source where positive terminal is connected to metal and negative terminal is connected to my p-type substrate, right? So then positive charges will accumulate on the metal surface, okay? So what this will do, this will repel the holes. So hole will start moving away, because holes are the majority carrier in a p-type substrate. Holes are basically moving away to this from this p-type silicon near oxide silicon interface. Okay, so that will leave behind negative immobile ions. Okay, so these are because if holes moves away from the interface, okay, then it will leaving behind all the acceptors. Those are, you remember, those are negative immobile ions. So we will have then a capacitor which is basically because of this depletion region, and this depletion region is forming because holes moves away from the interface and leaving behind this immobile ions. Okay, so now there is an electric field like this. So if we keep on increasing this voltage, then what will happen? Ultimately, minority carriers, those are electrons in the p-type substrate, okay, they started to attract and reach to this oxide silicon interface. So when the V is low, then when the V is low, then this negative charge will form by the acceptors here, okay, and when V is high, this negative charge layer will form by both electrons and acceptors, okay. These electrons are obviously minority carriers here, right, because it is a p-type substrate, so majority carriers are holes. But if you keep on increasing this voltage, then ultimately minority carriers electrons will be attracted and there will be a layer of minority carriers. So if I redraw this, yeah, yes,
Sir,
go ahead.
sir, can you go to the previous page?
Yeah, I'm redrawing it once more.
Okay, sir.
So this is my metal, this is my oxide insulating layer, and this is my p-type substrate. Now we have connected the voltage like this, where the metal is connected to the positive terminal of the battery, and p-type substrate is negative terminal of the battery, and these positive charges basically repel the holes, leaving behind so it will create a depletion region near this oxide silicon interface. So these are sorry so these are depletion regions. Those are basically because it is now void from or free from mobile holes, okay. So acceptors are here, and also there will be, if you keep on increasing the voltage as I mentioned before, then at some point minority carriers electrons will be attracted, okay, and they form a layer of electrons here, right. So if you keep on increasing your this magnitude of this voltage, the positive charge, amount of positive charge will increase here, and it will keep on populating more number of electrons in this oxide silicon interface, okay. So see, somehow if I can apply a voltage, if I can apply a voltage here, then we will be able to collect those electrons and bring back those electrons, right. So if I now somehow manage to connect a voltage source like this, we can drain out electron and we can source fresh electrons, right? So we can have a flow of charge or flow of current, right? The more the number of electrons, the more will be the flow of current, right? And less the number of electrons, less will be the flow of current. But what this additional voltage, so if I say this is my V1 and this is my V2, what this additional voltage will do, V2, it will basically drain out electrons and supply fresh electrons. What this V1 will do, V1 will decide how many electrons will be there, because the more the V1, the more will be the number of electrons, right? So V2 will help in flowing those electrons, and V1 will decide how many electrons will be there, because these electrons ultimately needs to compensate those positive charges present on the metal surface, because it is basically a capacitor, you see. So it is a capacitor that we have already mentioned. The electric field is like this, and because of this electric field, these electrons are basically accumulated. These electrons, in fact, known as these electrons, this particular layer is known as inversion layer. Inversion layer. Why it is inversion layer? The reason it is inversion layer, because you see this is a p-type substrate, so the majority of carriers are basically holes. So what you effectively needs to do, you effectively needs to form here electron channel. In other words, you effectively needs to form here an n-type kind of region, because where the electrons is dominating, right? So you are basically inverting this silicon substrate near oxide silicon interface. It is a p-type substrate, but by applying this voltage V1, what we are doing, we are inverting the nature of the substrate near oxide silicon interface. So near oxide silicon interface, it becomes as if it becomes n-type. So that is why the name is inversion layer, or this region is inverted, because we have applied voltage in such an amount which basically brings the minority carriers close to this oxide silicon interface, and as if it has made this region n-type, right? It is possible to draw the band diagram and show that it is indeed becomes n-type in this very close to this oxide silicon interface, but I am not very keen to draw band diagram here. That you will probably learn in your semiconductor device class. But you remember this, that the layer close to this oxide silicon interface is getting inverted. So if it is a p-type substrate, it becomes n-type, which will have electrons, and this number of electrons depends on what is the magnitude of this voltage V1, and if somehow we can apply a voltage source V2 between at the two sides of this electron layer, we will be able to take out these electrons and bring back those electrons through this terminal. Okay, so we will have a flow of current, right? Now we can have similar discussion if it is a n-type substrate, oxide, silicon dioxide, okay, usually silicon dioxide, a metal layer, usually aluminium. Okay, and say an n-type substrate. So now what we are trying to do, we are trying to apply a negative voltage to the metal and a positive voltage to the semiconductor. If you do that, you basically form negative charges at the metal surface. Those negative charges will basically repel electrons. So electrons move away because electrons are the majority carrier in n-type substrate, leaving behind positive immobile ions, say phosphorus, okay, or arsenic, right, because it is an n-type substrate. So this is immobile ions. Now these immobile ions is basically it is forming a depletion region, right, because it is depleted, this region is depleted or depleted of electrons, okay, or depleted of mobile charges, which is electrons in this case, because it is an n-type substrate. Now if you keep on increasing this magnitude of this voltage source, then more and more number of charges will form on this metal layer, which basically then attract minority carriers, which are holes, okay, minority carriers which are holes in this. So holes will be attracted and a layer of holes will form near this silicon oxide interface, okay. So these are holes. So in other words, we can again here say that this is an inversion layer, because the original inversion layer, because the original substrate was an n-type substrate, and I have applied the voltage in such a way and increase the voltage amount in such a way that holes are accumulated near this oxide silicon interface. That is, this region is now becomes p-type, okay. So in other words, this is form an inversion layer, or this part of the semiconductor is inverted, so it is no longer a n-type substrate, it becomes as if this region, which is close to oxide silicon interface, becomes a p-type substrate, okay, and it has holes, layer of holes. Now again in the same argument, we can say if we form a contacts and give and apply a voltage source, okay, then what will happen between these two region? If I form a voltage source, okay, then what will happen, that this voltage source will, this negative polarity will attract holes, the holes will coming out or drain out from this, and new holes will enter, okay. So we will have a flow of holes or flow of current. Again in the same fashion, we can say the more the magnitude of this voltage, the more will be the number of holes. So the amount of holes depends on this V1, okay, whereas the flow of current will be ensured by this voltage source V2, right. So in other words, we need two voltage sources. One voltage source is used to form an inversion layer, or to form a layer where we have mobile carriers. So these voltage source will ensure how many mobile carriers will be there, or the charge density of that channel. It is called channel. And the other voltage source V2 will ensure the drain out of those carrier and replenish of those carrier, right? So V2 will not ensure the amount of carriers. V1 will ensure the amount of carriers, right? I hope this part is clear to you, because this is forming the heart of the MOSFET operation. Now what we are trying to do, yes, please go ahead. Please go ahead.
Why can't we use p-type such that p side is connected to the positive terminal, and then like apply the same circuit, like then at the interface there will be holes like carriers. So we just want to make sure that at the interface there are carriers, so that we can produce a current through them, right?
Right. So if you are talking about this probably this diagram where we have accumulation, right? Accumulation of holes. Is that what you are saying?
So yes.
Yeah. So if we do that, we will see what modification we will make in actual MOSFET. But as you have pointed out, we can basically connect the same. We can basically have the same argument here and say that okay, why we can't apply a voltage source here and take those holes and bring those holes back. Now the thing is, if you do that, that movement of carriers will take place through the entire substrate, okay, and we will not have enough control over those carriers movement or the amount of carriers present there through this voltage. Okay.
Okay.
Let me repeat it once more. So if it is a p-type substrate and we want to have current by the holes only, then what will happen, even if we form an accumulation layer, but if we connect two terminals and apply a voltage and try to extract holes and bring back holes, the conduction of current will be through the entire substrate, because ultimately it is a p-type substrate, okay, and we will not have enough control over the amount of holes through this voltage V or V1 here, say it is V1, okay. Sir. And this is our V2. However, let me finish. However, if we manage to invert the channel, then in that tiny small region only the carriers will move. Rest of the substrate the carriers will not move, because in the rest of the substrate it is the minority carrier, where in that region we manage to invert the semiconductor. So if we have like a p-type substrate and use electron, or n-type substrate and use holes, in other words, say concentrate as it is as a p-type substrate. So if I have a p-type substrate and I manage to make a n-type region near this oxide silicon interface by applying a bias, then what I am doing, I am ensuring those electrons will move only through that tiny thin region which is known as channel, and we will not have any movement of electrons through this p-type substrate, because we have taken all the electrons over there. And we will see how those contacts will made and how we will ensure that electrons are no longer moving through the p-type substrate. That we will show you while we will discuss the structure in more detail. Okay. So yeah, please, someone else was asking something. Go ahead. Okay. So let's get, yeah.
Sir, so this.
Yes, please go ahead.
Sir, won't in the accumulation process would be higher? as compared to in the inversion one?
Accumulation process?
Sir, the
Amount of current you are saying?
yes, sir, amount of current. When the charges are getting accumulated.
There are two aspects. One is amount of current and one is controlling of current. We will see, because all we want to do, we will discuss that in detail. So all in the subsequent time. So all we want to do, we want to control the amount of charge through this terminal V, through this voltage V1, and that is we will see only possible if we invert the substrate. If we don't invert the substrate and try to use it as a accumulation layer, this control will no longer be there, and entire silicon substrate will carry current. We will see that that is not an effective approach. Okay, let me draw and show you how this exact. So this is just only metal oxide semiconductor. I haven't drawn the final MOSFET structure. When I draw the final MOSFET structure, it will be more clearer to you. Okay, so give me another 10 minutes. Now,
sir, so our main focus is controlling the current, not just.
Of course, yes, controlling the current and also getting a large current. We will see if we apply large voltage at that top metal gate, we will be able to invert that region even further, and that will give us enough number of electron. Okay, so let me draw the MOSFET. So far we are drawing only metal oxide semiconductor structure, but if we draw the entire MOSFET structure, it looks like this. So let's again start with a p-type substrate. Okay, I have a oxide layer on top of this p-type substrate. I have a metal layer here. Okay, now what I am additionally doing in MOSFET, I am creating N plus region here, N plus region here. Okay, I have additional metal contacts, one additional metal contacts here, another additional metal contacts here. Okay, so this terminal is known as source, this terminal is known as drain, this terminal is known as gate. So I haven't mentioned that terminal name as gate. Whatever we were discussing before, that top metal contacts is basically the gate terminal. Okay, and there is a substrate terminal also. In fact, we take substrate contact from the top because we can't take contact from the bottom, but for the time being, let's draw like that. Okay, so one is substrate contact, one is source, drain and gate contacts, right? Now, if we have such a device, I can draw I'm tempted to draw some other things also. For example, see, you have N plus P junction on the right hand side and also N plus P junction on the left hand side. So they will form a diode here and a diode here, right? That is one thing. We can also draw depletion region associated with these junctions. Let me let me just remove these diodes for the time being. But you remember there is two back-to-back diode, obviously, right? The reason I am removing it, I know it is difficult for you to remove, but you can draw it. You can draw it on top of your diode also. Just I want to want to make the drawing bit less clumsy, so I remove that those diodes. Okay, but there is two back-to-back diodes. Now if I draw the depletion regions, look at this PN plus junction. So there is a depletion region here. So one depletion region here. On the P side, and of course there is a depletion region on the N side, right? Of course N side depletion region width will be little bit less because this is heavily doped. The reason it is heavily doped, these two sides, because I am taking metal contacts. Okay, so these are metal contacts. This is metal contacts. We want to have ohmic contacts. Okay, we want to have ohmic contacts. It is possible to show if we have highly doped region, and if you then deposit metal on top of that highly doped region, and then it becomes close to ohmic. Let me repeat it once more. If I just in a semiconductor, on top of semiconductor, if I just deposit a metal, okay, and try to take a contacts, this junction, these contacts might not be ohmic. Okay, so what is the usual practice? Usual practice is do close to this region even further. So this is highly doped region, so that the resistance in that region is much less, and then you deposit the metal. Although it will be ohmic contact or not, depending on many other things like work function and all that of this semiconductor and metal junction, but let's just for the time being remember that whenever we deposit metal on top of semiconductor, we always put highly doped region. Okay, so that these contacts becomes ohmic. So we intentionally put N plus regions. Okay, plus means highly doped. Okay, so we have so this is effectively a 4-terminal device. One is gate, one is source, one is drain, and one is substrate. Right? Now, so these are depletion regions, obviously. And because these are PN junctions, any PN junction will have depletion region, that we know from our diode class. So there should not be any ambiguity. Now what we can do, we will extend this discussion in the next class also, but let me just start today. What we can do, we can apply a voltage at the gate, okay, so that it will form a additional depletion region, right? So what we can do, we apply a we apply a voltage between gate and source. In fact, source and substrate, we usually short them and put this to ground. So we are applying, effectively we are applying a voltage between gate and substrate. Okay. So this is basically our V1. You remember, we usually say it is VGS, gate source voltage. Okay. So if we apply that, what will happen? A depletion region is formed here. You remember, a depletion region is formed under this gate terminal, and this depletion region will contain acceptors because holes are moved away, leaving behind these acceptors. Okay. Now if you keep on increasing this VGS, when VGS is more than that of a voltage which we usually designate as threshold voltage, okay, when VGS is more than a certain voltage, that is threshold voltage, then a layer of electrons will form here. Right? A layer of electrons will form in this region. So this particular region is known as channel. Okay. As it is made of electron in this particular case, we can say it is N channel. Okay. If instead of electrons it is made of holes, we can call it P channel, right? But when it is a p-type substrate, the channel will be formed with electrons, so it is an N channel or N channel device, right? Then what we are now going to do, as I mentioned to you before, we now apply another voltage source. I have hardly place to draw it. So I am now applying another voltage source between, again, source and drain. Okay, between, you remember we mentioned that if we somehow can apply a voltage source between this channel and try to take those electrons and bring those electrons back. So what we are doing, we are adding this another voltage source which is known as VDS, which is connected between drain and source. Okay, and this drain and source, so these two voltage sources you see with respect to ground. Okay, so source is grounded, substrate is grounded, and we have two voltage source, one between gate and source and another between drain and source. So if we have VGS more than VTH, okay, there will be channel is formed because the substrate is now inverted, and you see we can't take those acceptor or immobile ions, we can't take those immobile ions through this drain terminal, right? All we can do is to take these mobile charges, that is electrons in this case. So we will take these mobile charges through this terminal, drain terminal, that is how the name came, it's drain out carriers. Okay, and this terminal source through which new electrons will come to this channel, because this battery will supply new electrons. So these electrons will come and replenish this channel. So it will basically sources, so that is how the name came. Source is basically sourcing the carrier and drain is basically draining out the carrier. And what this gate will do, gate will ensure, or this gate voltage VGS will ensure how many electrons will be there. If you increase this VGS even further beyond this VTH, the number of electrons will increase. Okay, so now you have more current. If you increase VGS even more further, then it will be more bended, the bands will bended more, it will be more inverted, more number of electrons, so we will have more current. Okay, how this characteristic of current voltage looks like, we will discuss this in the next class. How about the, you might argue with me, what about the flow of current in the substrate? You see, this junction is reverse bias, this drain and substrate is reverse bias, because this is N plus is connected to positive and this p type substrate is grounded. So if you look this junction carefully and try to draw this depletion region once more, this depletion region will remain the same width, whereas this depletion region near this drain is much more, because you have reverse bias this junction. So there is no way current can flow between drain and substrate or between source and substrate, because between source and substrate there is no, it is both are shorted and forming these, both are basically grounded. And what about drain and substrate? It is highly reverse bias. So there is no current between these terminals of these two terminals of MOSFET and the substrate. However, there was back-to-back diode, and we have removed that back-to-back diode at least in this channel. So we have now a channel, the continuity of the channel is made available by this N plus region. Okay, if instead of N plus, if you put P plus, then this device will not work, you see. So we have intentionally made N plus regions so that we will have ohmic contact and we have continuity of this channel. So we have N plus, through this N plus region electrons will go to this supply and come back through that supply through this N plus source and coming back to this channel. So this is how this device works. We will stop here today and we will again try to explain this operation in tomorrow's class. Okay, so if you have any queries, we can quickly take one or two questions. Yes, sure.
Sir, what is the use of this oxide layer? Is it simply an insulator or there is any other purpose also?
No, this is oxide layer which is form this capacitive action, because you see these oxide layer, because of this oxide layer, the top metal layer and below this electron channel, they are forming basically effectively two charging layers. Okay, and this oxide layer is effectively form this electric field, which is basically allowing the formation of this negative mobile charges. So without this oxide layer it will not work. If instead of oxide layer, if you form directly a metal layer on top of that, whatever carrier is there, it will go to the gate. So through this oxide layer we are ensuring a capacitive action, and we can reduce the oxide layer thickness to improve this capacitive action even further. But we can't do it.
Okay, sir.
Yes, Harsh. Yes, Harsh.
Sir, can you please explain once again why the current will not, electrons will not flow between source and substrate?
Yeah, the source and substrate, the electrons will not flow, because you see in the source and substrate there is depletion region, and I haven't applied any bias. I have to apply 0.7 volt between source and substrate, so that these electrons can flow between source and substrate. What about drain and substrate? Anyway, it is highly reverse bias, so there is again no flow of current. Okay. So between source and substrate I need to apply at least 0.7 volt, where I am applying 0 volt basically, and between drain and substrate I am applying reverse bias, so there is no flow of current between those.
Okay.
Yeah.
Sir, one more thing, will that drain and substrate border increase in width because of reverse bias?
No, not border. Yeah, depletion region width will increase. So we will discuss that again tomorrow. the depletion region with initially same when we haven't applied any bias, but if we applied bias, the depletion region near drain substrate will increase, because obviously it is a reverse bias, but this source and substrate depletion region will remain intact because I haven't applied any reverse bias here. But here without any biasing, this because source and drain are basically interchangeable, I mean the doping concentration is same. Okay, so same terminal you can use source or same terminal you can use drain, but the depending on this supply voltage, the drain and source will be defined. Now the thing is, as you are applying reverse bias here, once you are applying the bias, the depletion region will width of the depletion region will increase at drain substrate side. Okay, yeah. So yes, Harsh or Shreyan, yeah.
Sir, what do you mean by that ohmic contact? Like by using that N plus, you're decreasing the resistivity of that area. Like what exactly?
Right. So I'm buying. So usual practices. It is also possible to show, but I am not going in that direction. The usual practice is we always put, whenever we put metal on top of a semiconductor, we usually dope the region near that contact heavily. Okay, so that this region becomes the resistance of this region becomes, or resistivity of that region is much less than that original semiconductor. So here if this resistivity is rho s and here it is rho s1, usually this rho s1 is much less than rho s. Okay, resistivity. So if that is the case, when we deposit metal, this junction, the formation of these metal contacts is ohmic. So if I put IV of this in this contacts, we will get almost linear situation. But if we don't put this heavily doped region, it acts as a like a kind of a diode, Schottky diode. So you will not get ohmic, you will get diodic nature. Okay, so you will get exponential kind of IV. Right, so the usual practice is always put heavily doped region. Here intentionally we put N plus instead of P plus, because if you put P plus, you see it is not working. Right, anyone else? Okay, so we'll stop here. Yeah. Yes.
So when the channel is in contact with either of the source and drain highly doped regions, they act
Yes.
as like one region. So in order for the electrons from the channel to flow into any of the drain or source regions, they need to be less have less electrons. Because there's no drift in that region, it will only be diffusion for that part, right?
No. Sorry, I didn't understand the fully what you are saying. Why it is highly doped, or why there is a connection between N plus and this channel? Is that what you are asking?
No, my question is that when electrons will flow from, say, the channel to the drain, then will it primarily be drift, or will there be a major
it is drift. It is drift because we are applying a bias, so it is drift.
So diffusion will be negligible.
No, it's not diffusion, it's drift.
Okay. Thank you, sir.
Yeah. Josh, yes, Josh, yeah, go ahead.
Sir, will there be any significant change in the functionality if we reverse the polarity of VDS?
If you reverse the polarity of the VDS, you have to you can reverse the polarity of VDS. Then you have to take basically this gate voltage. I mean, this negative terminal you need to connect here. So, and this needs to be connected to the substrate. What I am saying that effectively then it is your drain, it is your source. Okay. Is that answer your question? So what I mean is, say what you are saying very quickly. If you are saying, okay, what about if I have this voltage source where it is like this. This is what you are saying. Okay. In that case, this is your drain and this is your source. Okay. The reason I am saying this, then you put your this voltage with respect to this source. Okay. So you are basically swapping. So because drain and source terminal is identical, you can swap them, but you this biasing then always with respect to source, because what you are ultimately doing, you are basically shorting the source and substrate and grounding it. Okay. So you are basically swapping everything then, if that answered your question.
Yes, sir.
Okay. Okay. So thank you very much. I am closing the session. Okay.